Hello everyone. In this video, we are going to talk about shear stresses in beams. So we learned that if the beam goes through non-uniform bending, which means there are vertical forces along the beam, then moment is not going to be constant, and also anywhere you cut along the beam, there will be shear stress and there will be shear forces like this V. So because there is shear force V, there will be shear stress tau on this section. And now the question is, what kind of distribution does this tau have with respect to the location along the beam, in this case Z and Y, specifically Y, because we'll see that Y is the one that matters here. Okay, so if at location X we know V of X, then basically how much is tau as a function of Y? This is what we are after. And this is not in general a super easy topic to derive the equation for. For rectangular cross sections, it's much easier than the other ones. So we're going to focus first on the rectangular cross sections. Now, how do we know there is shear stress on the cross sections? Well, that's obvious because of the free body diagrams, right? So if you have a beam like this, and wherever we cut, we know there is, for equilibrium, there is shear force. But also here we claim that not only there is shear force in these vertical sections, there is shear force also in the longitudinal direction. If you look at anywhere along the longitudinal direction, there is also shear stress. If you look at this diagram, you've probably seen it, right? That if I look at some small element here at some height y, and if I look at it, not only there is tau in this direction, there should also be tau in this direction. Now, of course, it should be, otherwise this element will go through a net moment and will spin. Okay, and this one is in the x direction. So there is clearly shear stress in the x direction, but physically, how would you experience that? Well, if you make a beam out of plywood or several different basically components, longitudinal components, and glue them together, or let's say not just glue them, just put them on the top of each other and apply this shear force, you're going to see that they are going to slide with respect to each other. So there should be some shear force, and as a result, shear stress causing that longitudinal sliding. Okay? Now, how do we formulate it? So to do that, first we look at a small infinitesimal element with length dx somewhere along the beam at location x, and this is the side view of the beam, and this cross section is shown by points nm, n1, and m1. Now on the left side there is shear force V and bending moment m. On the right side is V plus dV and m plus dm. Clearly, because there is shear force, the V and X and M, these are functions of location and they are not constants. It's non-uniform bending. As a result, if the left side has V and M, the right side should have something a little bit different, and we showed those differences by dV and dm. Okay? Now, what we do is, we know because of the bending moment, there is clearly normal stress on both faces of this element. So on the MN face, there is basically normal stress, and on the right side, there is also normal stress. Now, of course, here on this middle line, which is the neutral axis, and for a rectangular section, it's in the middle, there is no stress, and you can see that at the bottom, there is tension, and at the top there is compression, and that's because of the direction of the M. So it is going to bend this way, and on the top clearly there is shrinking, on the bottom there is expansion, and so this is the stress distribution. Okay, and sigma 1 and sigma 2 are different values, of course, because they depend on the x. Because remember, sigma, if you remember, it was negative my over I, and so since m is a function of x, sigma is going to be a function of x. Okay, good. Now, what we do is, we know sigma 1 and sigma 2 are not the same because there is some length difference between them. So now what we do, we break this element into even a smaller portion of it, and we cut it at height y1, or arbitrary y, and we only look at this top portion of this element, which is shown here. So this element Pm, P1, M1, okay, where the bottom of it has height y1 from neutral axis, and the top of it is, of course, h over 2, where h is the entire height. So clearly, because sigma 1 and sigma 2 are not the same, some of the forces in the x direction will not be zero. You need some force here and some shear stress to basically create equilibrium. And assuming that sigma 2 is bigger than sigma 1, or sigma 1 in this case bigger than sigma 2, then tau is going to be positive, otherwise it's going to be negative. But it has to exist anyways. Okay, so now, as I said, some of the forces in the x direction, in this direction, should be zero. So sum of sigma, integral of sigma 1 over this area minus the sigma 2 over this area plus the shear force over this one is going to be zero. So A1, A2, and A3, you know which one we are talking about, right? This is A1, this is A2, and this bottom one is A3. This has to be equal to zero. Now, sigma 1 is my over I, and here we are talking about their magnitudes, and sigma 2 is m plus d my over I. And you might say, why magnitude? Because the directions are already considered here with the positive and negative sign. So what we really need to look at are their magnitudes. And if we simplify now, remember in this case, A1 and A2 are the same cross section. Okay? So if we plug in those and simplify between sigma 1 and sigma 2, because the dAs and the areas are the same area, then these two, right, it's going to be my over I minus m plus dmy over I. When you do that, the m term would cancel, and all you will get is basically negative dmy over I integral. And then when that negative term is taken to the other side and set it equal to tau, clearly you see tau is going to be what? So clearly there is some, let's clean it up a little bit. So as I said, if you simplify these two and take it to the other side, what do we get? We get integral over A3 of tau dA is equal to integral over A1 or A2, doesn't matter, they are the same thing, of basically dm and then y over I. Correct? So that's what you have over here. And now we have to calculate this integral of tau. By the way, there was some dA on this side too. So now what I do is, from here, this dm does not depend on y, and this I does not depend on y. So I bring it out. It's going to be dm over I integral of y dA. And tau, if you look at it, this area A3 is what? If you assume that this tau is constant all over this length, so this integral is going to be basically tau times what? Area A3. And area A3 has the length dx and the width b, so it's going to be b dx. Okay, and then if you need tau, you need to divide both sides by b dx. So you bring a b and you bring a dx, and that is going to be this formula that you can see here. Now, dm over dx, the derivative of moment with respect to position, that's the shear force at that location. That's v of x. Okay, we know this from the shear force and bending moment diagrams. If you go and look at my video where I explain these and how to get them, you know v is derivative of m with respect to x. So that's v. IB is there, and then this integral of y dA, that's the first moment of area, correct, for this green dashed surface. And so if we call that q, if we call this integral, this first moment, call it q, tau is going to be VQ over IB. So that important formula, tau VQ over IB, is the one we are going to use for rectangular cross sections. Okay? Where V is the shear force at that location, and I is the total moment about the neutral axis, in this case IZZ. correct? So this I is I of ZZ, B is the width of the beam, V is V of X, and Q is this entity here, which is clearly a function of Y, okay? So you see, really your tau is both a function of X and Y, depending on where you cut it and where along the section you calculated. It's function of both. Okay, and from this moment, if you look at this moment, you clearly can see that Q, which is the area of this cross section here, the first moment of this cross section, clearly the bigger this y1 is, or y is, this area is going to be smaller and smaller. So if y1 goes to h over 2, this area will literally be 0. So at the very top of the cross section, tau should be 0 because Q is 0. And when at y of 0 you have half of the surface, that is your tau max because your Q is max. Okay, so clearly Q depends on the location, and this is what you can see over here. If we want to calculate for a cross section, a rectangular cross section, we want to find Q. Q is integral of y dA, where y, or y1 here, is integral of y dA, where dA here is basically an element like this. It has width of b, it has thickness of dy, so that is the area. The height of it is y. As I said, the thickness is dy. And then, since we only want it for this blue section, y should change from y1 to h over 2, which you can see here. And clearly it's going to be a quadratic term, and as you can see, this is going to be your Q. As you can see, it depends on y1 squared in a negative manner. So at y1 of 0, it's the maximum, and at y1 of h over 2, it's minimum, which is 0. So shear stress changes quadratically with respect to the y. At the neutral axis is max, and at the very tops, they are 0. That's exactly kind of opposite of the normal stress. If you remember, normal stress was maximum at the bottom and top, and 0 at the neutral axis, with one difference. Of course, sigma was changing linearly. If you look at it, sigma changes linearly, but shear stress changes in a quadratic manner. And of course, the maximum, if we want it, we have to set this equal to 0. And if you do so, your Q is going to be BH squared over 8. Okay. And then I, remember I for this cross section with B and H, it is BH cubed over 12. And this maximum happens at y1 of 0. So if you plug in and simplify, you're going to get this relation. And if for I you plug in that top relation, your maximum stress is 3V over 2A. Okay, so remember, at this cross section, the shear force is V. So if you divide V by the whole cross section A, you expect that is the average shear stress on that plane, because the distribution is not uniform, correct? So if you divide the entire shear force by the entire cross section, that would be the average tau. But at the neutral axis, it's 3 over 2. At the top points, it's 0. So your tau max is 1.5 watt tau average. Okay? And this is a formula that we use a lot. By the way, one other thing we have to pay attention to is when there are shear stresses, if you look at these elements that were originally, or these planes, these cross sections that were originally normal to the neutral axis, now because there is shear stress in this longitudinal direction at any point underneath these elements at different points and different values, then because of that, because of these shear stresses, these elements, these points on this cross section will move differently in the x direction. So your cross sections after deformation will not be at 90-degree angle with respect to these longitudinal lines. While in pure bending, if you remember, let's see if I can find it. In pure bending, we said that that is the case, correct? Let's see if here, there we go. If you remember, I said in pure bending, these cross sections will always stay at 90-degree angle with respect to the longitudinal lines, but not in non-pure bending. Because of the shear, they're gonna deform like that. Okay, just keep that in mind. So now let's go ahead and look at one problem here before we look at another type of cross section. So here we have a wooden beam with dimensions B and H, okay, where they are 100 and 150 mils, and it's simply supported. There are two concentrated loads here and here, kind of symmetric at distance A, and A is also given to you. And what we need to do is, for this beam, the maximum allowable normal stress is 11 megapascal, and the maximum allowable shear stress is 1.2 megapascal. Okay? So we want to know for this beam, how much is the maximum force, if they are the same force, how much is the maximum P that you can possibly apply to the beam here. And when I look at it also, I do not see any basically length for the beam, and it's probably because you don't need it, as we'll find. So the first thing to do is to find the M and the V diagrams. So using those, we can look at the sigma max and the tau max. And in this case, it's a very simple case. It's symmetric. So clearly there is a P force here and there is a P force there. That's all it is. Okay, it's perfectly symmetric. There is no horizontal force needed here. And if we draw the shear force and the bending moment diagrams, what would we get? So here could be a plot of V versus X. And right below that, we can plot M versus X. Correct? So remember how we get the V and M, right? Wherever we section on the right side, V is downward and M is upward. So if we come here and cut at this location and put some V and some M, and look at the left side, clearly V has to be equal to P, and M is going to be, if this distance is X, M, if you take some of the moment about the section points, M has to be equal to PX, correct? So V is P. And remember here, look back. So you can watch my video, but remember dm over dx is V. So if V is constant, that's derivative of M. So M has to be a line. So derivative of that is V. So if V is P, then M should be P times X, like this. And it goes on until you get to the distance A. So this is P, and it goes here. And that value, of course, should be P times A. Then between these two cross sections, what happens? If you cut here and look at it, now if you look at this V down here, on the left side of it, there is a P up and there is a P down. So V should be basically 0, right? And then the other side of your, if you look, once you pass it again and draw another V, this time there are two P's down, there is one P up, so this should be negative P. So it goes 0, and then at this other A, it goes to negative P, like that. So let's say the whole thing is L, which we don't, by the way, care, but this is A, this is basically L minus A, and this point here is L. Okay, so if you look at your V diagram, you basically have this kind of step behavior. Now here is 0, that means it's going to stay constant, and then it's negative, so it's going to go back to 0 at this end because a roller or a pivot does not have any moment, so you go back to 0 like this, so you get a trapezoid. So now if you want, your maximum shear force is clearly V, and your maximum moment is PA, correct? P and PA. So let's write them down. V max is P at any location on the beam, and M max is P times A. You see, they do not depend on L. That's why you don't care about L in this case, because the shape is perfectly symmetric. So now with those in mind, we have to go ahead and find the values. So clearly cross section here is B times H, and I is B times H cubed over 12, correct? If that's the case, we can say that sigma max is M max times Y max over I, where I max is simply H over 2, M max is PA, I is what you can see here, BH cubed over 12. So it is going to be some function of P because A, H, and B, they're all given. On the other hand, tau max, if you remember, it was 3 over 2 V over A. Now, if this is max, V has to be max, where V max is P and A is B over H. So again, you see that is going to be a function of P, right? So if we write them, now how much are they? Well, your sigma max at max could be the same as sigma allowed. So this guy should be 11 megapascal, and this other one should be 1.2 megapascal. And from there, I can find two numbers for P, or P max in this case. So the top one will give you a P max of 8.25 kilonewton. And the bottom one will give you 12 kilonewton. Which one would you pick? Remember, you always pick the smaller one, so no failure happens in bending or shear. So here you see that the bending is dominating, okay? And you have to go based on the bending. Okay, so this is how you deal with non-uniform bending by considering both normal stress and shear stress. Now, this was really good for rectangular cross sections. We got what we wanted to get. We had the formula here, right? And the question is now, what if your cross section is not rectangular? Is there anything for that? And the answer is it's not necessarily easy for other cross sections to get a distribution function, okay? But we can find values for max. We can approximate the max values. So throughout the entire section, as I said, there is no simple way to find the shear stress distribution as a function of y, because here the reason is if you go up and down on this and you look at this guy, it's not as easy, right? You have, if you look at the this portion and you look at the distribution, first of all, the bending on this is not as easy, okay? And the bending force that depends on y, clearly, if you look at the element, the sides of this face are not rectangular like last time. The stress is applied to this curve, And also Q for this guy is not just a simple function because you're dealing with the cross section of a circle, and a section of a circle, I'm sorry. And it's not like it's just one dimension of it that changes. In both dimension it is changing, so it is very complicated. But if we want to approximate based on this formula, that is really cross section of circle, rectangular. If you want to approximate with this, I for a circle with radius r is pi r to the 4/4, and q max, which happens here for half of the circle, is basically the location of the centroid of it times area of it. Remember, this q is integral of y dA, and that is equal to y bar of that surface times a of that surface. So if I consider half of this, the area of it is, of course, pi r squared over 2. And remember, the centroid for half circle or quarter circle, here this distance is 4r over 3 pi. So that is going to be Q for it, and B, the width of the beam at the middle is 2R. So if you plug in, you can find is 4/3 over VA. And remember, V over A is tau average. So 4/3 tau average is tau max for circular. For rectangular, it was 3/2. And if the cross section is a disc or a donut like this, and you have radius r1 and r2, then I is this, Q is this one, B is this one. Again, you can find something. This time is 4/3 VA, but times another parameter here, which depends on the two radii. Now, if R1 is 0, you get back to this whole ratio should be 1, right? If R1 is 0, look at it, you get 1. But if R1 is not 0, this ratio is not going to be 1. So it's going to be 4/3 tau average times this ratio, which depends on R1 and R2. So that is for a circular cross-section that is hollow. And if the rectangular cross-section is hollow, still you can do that, okay? Still you can do that. Still the max happens here, with the difference that now your Q is going to be for this guy here, okay, which you have to find the centroid of it and multiply it by the area to get the Q. I is still the same I, except this hollow part should be subtracted. And B is going to be this thickness. If this thickness is T, is going to be 2T. Okay, so based on that, you can still plug it into this VQ over IB. Remember, this is the most important formula that we have, and plug it in here and you can find it. And for more complicated cross sections, it is even harder than this, so we're gonna stop it right there. Okay, hopefully this material was useful to you. Remember, my material are all coming from The Mechanics of Material by Giray and Brooks, which is a great book, and it's good to have it in your library. Hopefully the video was useful to you, and I'm gonna see you in the next video. Thank you.